Hello everyone. So today we're going to talk about synthesis of aldehydes and ketones. First we're going to go over all the reactions and then we'll move on to new reactions. So I'm going to go in the order in which we've learned about ketones and aldehydes from Chem 105 and beyond. So from chapter 8, this is where we learned for the first time how to make ketones and aldehydes, the reaction from alkenes and as you remember, we could oxidatively cleave the alkene into ketone and or aldehyde depending on the type of substitution on the around the double bond. Now, because now we are synthesizing the aldehydes and ketones, we want to get as clean of the product as possible. So in this case, we're going to look at symmetrical alkene to produce a ketone or an aldehyde. So let's take a look at that. Let's go to our beautiful blue color here. Okay. Let's first synthesize ketones. To synthesize a ketone, I'm going to take an alkene that is symmetrically has symmetrically substituted positions on both sides. So for oxidative cleavage of the alkene, I'm going to use the either azonolysis reaction, or I can go into a harsh oxidative cleavage. Okay. For ketones, we can use mild oxidative cleavage, which will be the azonolysis reaction. Ozone in dimethyl sulfide. Okay. And the result of this reaction will be formation of 2 moles of a ketone. The substituents on both sides are the same, so we're going to get 2 moles of the same ketone. Okay? However, if we are making an aldehyde, we will start with the symmetrical alkene again, but we want to make sure that one of the positions on the alkene is still not substituted. So, and the presence of these hydrogens will be very important. And the type of the reactions that we will perform will also be very important here. So in this case, we could use only mild oxidative cleavage. Dimethyl sulfide. And the result of the reaction will be, as we remember, two equivalents of an aldehyde. Okay? So this reaction, just to remind you, was the oxidative cleavage. Of alkenes. And as I've mentioned, for ketones, you could use mild or harsh conditions. And just to remind you, the harsh conditions, it's going to be hot, acidic, concentrated KMNO4 solution. Okay? So for ketones, we can use hot acidic concentrated KMNO4, and for the aldehydes, only the mild conditions. Okay, and this is it for the chapter 8 synthesis. Let's move on. The next chapter in which we saw the synthesis of ketones and aldehydes was chapter 8, and that is from alkynes. Okay? And in this case, again, we have to be very careful with the compounds that we will be making. So let's take a look at that. If you remember from the reactions of alkynes, the reactions were very clean with the terminal alkynes. That would give you a clean major product, in which case you can ignore the formation of minor product. So let's see, if we want to make a ketone, then for synthesis of ketones, we're going to take a terminal alkyne. Let's bring in a hydrogen on the terminal carbon. And we will react the terminal alkyne under acid-catalyzed hydrolysis of alkyne, mercury chloride, HCl, water, a little bit heat applied. This reaction goes by Markovnikov path. So among those two carbons, this carbon is substituted, and it will be taking the carbonyl. Let's number the carbons throughout the compound. 1, 2, 3, 4, 5, 6. So the product of the reaction will have 6 carbons. So our carbon number 1, carbon number 1 and carbon number 2 are the ones that are involved in the reaction. And according to this reaction conditions, we're going to get a ketone on position number 2 as a major product. Now remember, we're synthesizing the compound, so we want to get as clean of the yield as possible. Okay? If you don't have a terminal alkyne and you want to make a ketone, you have to worry about the substitution type on two sides. You're going to get two products in pretty close yields, so the cleaning up will become pretty tedious. So let's take a look at that. So if it's an internal alkyne, and let's just make up that alkyne. So in this case, I again would like to take a symmetrical alkyne so I could get one product only, okay? Because the substituents are pretty much the same. So these two positions are carrying the same substituents. So if I will be reacting this compound with acid catalyzed hydrolysis conditions, let's let's number the carbons. 1, 2, 3, 4, 5, 6, 7, 8. We're going to get a product with, it will be octanone, and let's take a look at the outcomes here. 1, 2, 3, 4, 5, 6, 7, 8. So we're going to get a carbonyl on position number 4. That's your red carbon, okay? And then because the substituents were identical, you are going to get 2 equivalents of the compound. I'm going to put it underneath so you can clearly see that it's just the same compound. So let's number again. 1, 2, 3, 4, 5, 6, 7, and 8. And we could put the carbonyl onto this position, but it's just the same compound. If you count the carbons from here, 1, 2, 3, 4, your carbonyl is residing on position 4 from the right, 1, 2, 3, 4 on position number 4 from the left. So it is the same molecule. So you don't have to write this down, okay? So your correct answer will be this. Okay. Now, if my goal is to prepare an aldehyde, then I will have no choice but to go only after the terminal alkyne. Okay, and we're going to use anti-Markovnikov reaction setting. So let's put the reaction conditions. Two asymmetric carbons. This carbon number 1 okay, 1, 2, 3, 4, 5, 6. Okay, your carbon number 1 is less or not substituted, and that is going to be the carbons that will get oxidized under anti-Markovnikov conditions. We're going to use dicyamyl borane in THF, which will be followed by treatment with hydrogen peroxide under basic conditions. The outcome of this reaction is going to be an anti-Markovnikov product where oxidation will happen on the terminal position. Oops. 4, 5, and 6. So carbon number 1, carbon number 2, and in this case, let me move the molecule a little bit aside. Your carbonyl will be formed on position number 1, and it will be an aldehyde. Okay, and in this case, we're going to form just the one molecule of it. Actually, I've made a mistake here. I'm going to make just one molecule just one equivalent of the compound from internal alkyne as well. Okay, so let's identify here that these are the same. Okay, so chapter 9 material is covered as well. So next thing that we're going to go over is from chapter 11. Let's flip the page. And this will be the oxidation of alcohols. Okay. We've learned from chapter 11 that we can oxidize primary and secondary alcohols only, and depending on the reaction conditions, the oxidation will go towards formation of aldehyde, of ketone or aldehyde, or a carboxylic acid. Tertiary alcohols are not going to be oxidized, so primary and secondary alcohols. So we're going to start with the synthesis of ketones. Your ketones cannot carry carbonyl on the terminal position, so the oxidation will happen from the secondary alcohols. Reactive carbon is a secondary carbon. So we could use, in this case, mild or harsh oxidative conditions. Okay? And let's make sure that we remember all of the conditions for that. So for mild conditions, I'm going to put it down here so we will have a little bit more space. For mild conditions, we could use either PCC in DCM. I want you to recall the reagents for PCC. It's chromic oxide, okay, pyridine, and hydrochloric acid, and the reagent is in dichloromethane, okay. Or we could use Swern reagent, okay, for which we would use oxalyl chloride, as you remember from Chem 105. DMSO, T, and the reaction was done at minus 70 degrees Celsius. Okay? So those are mild oxidative conditions. For harsh oxidative conditions, let's separate those two. For harsh oxidative conditions, we could use either one of these reagents. So I'm going to put asterisks, concentrated nitric acid, hot KMNO4, concentrated. We could use chromic acid, we could use Jones reagent, HCl, acetone, 0 degrees Celsius. Okay? Any one of those conditions will provide oxidation of a secondary alcohol into a ketone. Okay? So I'm not going to put reagents here. You can use any of those sets. And as you remember, we've shown it in Chem 105 that for oxidation to a ketone, if I put my oxidative reagent, oxygen, in brackets here, as you remember, we needed an oxygen, and from the reactive carbon position carrying hydroxy group, we needed hydrogen of the carbon and also hydrogen of the hydroxy group. And that pairing with the oxygen of oxidizing reagent would give us a product. Okay? Now, this is a setting for oxidation of secondary alcohols. They will make ketones. However, if I need to make an aldehyde, I have to pay very close attention to my reagents. Okay, so for ketones, aldehydes, my apologies. Are produced from primary alcohols. Okay, and we would have to use only mild conditions. This is a primary alcohol, and only mild conditions will give us an aldehyde. And again, remember, for forming a carbonyl, we would need oxygen from oxidizing reagent, hydrogen from hydroxy group, hydrogen from your reactive carbon. And if you're using mild oxidizing agent, you're going to get an aldehyde in this case. But if you used harsh reagent, so this is an aldehyde, but if we used harsh oxidizing conditions, first you will get the aldehyde as well, but we still have a hydrogen residing on our reactive carbon. Okay, so under harsh conditions, we will get oxidation further, and we will produce carboxylic acid. And because that's not the goal, we want to go with mild conditions only. Okay? So what other reactions have we learned so far? Let's make sure that we're not forgetting any of those reactions, okay, that we have already investigated. So what else did we have? We can go from the Friedel-Crafts acylation reaction. Let's take a look at that. And it will be our chapter 17. And as you remember, the reaction conditions were specific for forming aldehydes. So again, let's put ketones are produced by reacting benzene with acyl chlorides aluminum chloride is used as a catalyst, we can follow up with cleaning the water-soluble residue from the reaction mixture. That's not a mechanistic step. So we're using acyl chlorides to produce a ketone. Okay? But let's remember also that if we want to make the aldehyde, aromatic aldehyde, in this case, the acyl chloride is not going to be stable, so we are producing in situ the precursor for an aldehyde. As you remember, this was the reaction. We used carbon monoxide, HCl, cuprous chloride, and the outcome of the reaction was formation of an aldehyde. Okay? Moving on. Where else can we gather the information for formation of the ketones? Okay, so this reaction will be just for synthesis of ketones, and where we can get the further information for this reaction is the reaction of Grignard reagent with the aldehydes to produce an alcohol and then convert it into an ketone. So ketones, let's put synthesis of ketones. From aldehydes. That is an indirect path. So let's take a good look at an example. If you have an aldehyde, you can first react your aldehyde with Grignard reagent. Diethyl ether. Of course, you can substitute your Grignard reagent with organometallic lithium, doesn't really matter. Second step, dilute acid to form an alcohol. We will form racemic mixture of enantiomeric alcohols. This is a secondary alcohol. So we start with aldehyde. In first and second step, we convert it into secondary alcohol, and then we can reduce it, we can oxidize it with PCC, DCM, and produce a ketone on that reactive position. Okay? So once we did that, we're going to go through some practice problems, and then I will give you some practice problems to work on your own, and that will conclude this lecture. Okay, so let's do a couple of practice problems. Let's synthesize the following ketones from different sources. A. How can we make this compound? Let's characterize it. This is a ketone. And let's see from how many different sources we can make this compound. What will be the sources that will be useful for making this compound in good synthetic pathways? Let's identify the reactive carbon, identify the surroundings of this carbon. On one side, I have a cyclohexyl substituent. On the other side, it's isobutyl substituent. So if I want to make this compound from an alkene, let's try that. I need to put together a precursor for that product. And the way I will do that is the following. I'm going to redraw my molecule, and my reactive carbon is the one that will carry a carbonyl in the product. So if I want to make it out of alkene, I want to make my alkene as close in its structure to the product as possible, and I don't want to get any of the byproducts after the reactions that I would have to clean up my reaction after. So I'm going to use this alkene for a very simple reason. If I apply harsh oxidative cleavage here by using hot concentrated KMnO4, the cleavage will give me a ketone on one side, and that would be the molecule of interest. And the byproduct under harsh conditions is going to be carbonic acid, which will fall apart, as you know, into carbon dioxide gas and water. So it looks like we're getting clean product after this reaction. Okay. So what other method could we use in this case? Now let's see if I can produce it from an alkyne. Remember, if I'm producing it from alkyne, I'm not cleaving my triple bond completely. I'm just oxidizing one of the carbons on the sp hybridized junction. So again, if I put my target molecule out there, it carries off of the cyclohexyl residue, it carries 1, 2, 3, and 4 carbons. So let's put that chain out, 1. And because we are carrying a carbonyl on this position, right on this carbon, I'm going to place my triple bond. And then off of this triple bond, I'm going to draw the next carbon and the isopropyl residue on. Okay, so what conditions would I like to apply in this case? Since I'm putting the carbonyl on this position, and that position is closer to cyclohexyl residue, my cyclohexyl residue is a little bit more crowded than the isopropyl. I'm going to apply the reaction conditions where I will be getting a little bit more of the more substituted product. So if I apply Markovnikov rule, Markovnikov setting, I'm going to produce a product in which on the carbon closer to the cyclohexyl residue will form a carbonyl. My blue carbon will acquire 2 hydrogens, and then we will get the isopropyl residue off of it. This is not going to be the only product. I'm going to end up with a mix of the products. I don't have a symmetrical alkyne, so in this case, I'm going to get a mix of the products A and B. If I predict the reaction outcomes here, I'm going to get maybe 60% of A and 40% of B. And that is not a good synthetic strategy. So if I had to stick in with one of those two strategies, indeed I would go from the alkene. But let's see if we can apply a different method here. Since I'm forming a ketone, I can start from the secondary alcohol, carrying hydroxy group on that reactive red position. And I can oxidize it. I want to be mild if I can, so I'm going to oxidize it with PCC and VCN and turn it into a ketone. And if I didn't have the alcohol, I could start from the aldehyde and in this case, as we can see for the target molecule, I could take this aldehyde or I could take this aldehyde to begin with. Okay, we're going to take one of those scenarios. My aldehyde will react with the Grignard reagent, or let's use organometallic lithium this time. So let's put the target molecule down here so we will have a good visual of this. If I'm using for the aldehyde this portion of the molecule, then my Grignard reagent is going to carry the isobutyl residue or my organometallic lithium. So it's going to be either Grignard reagent or organometallic lithium. THF, second step H3O plus. Okay, we will get a secondary alcohol. Of course, my alcohol will be a racemic mixture. And after that, we could just go to the synthetic step. Okay? So hopefully this was a good preparation for you. I'm going to put a couple of compounds for you and see if you can synthesize those compounds by the old techniques. Okay. A, B, See? And D. And that will be it for today. Thank you for watching, and we'll move to the next video